60 Minutes Rewind.
The Large Hadron Collider is one of the wonders of the modern world. It's believed to be the largest and most complex machine mankind has ever created. Buried hundreds of feet beneath Switzerland and France, the collider smashes subatomic particles together with enormous energy. By studying the collisions, scientists have already made a major discovery, the Higgs boson. Some call it the God particle. They're now hoping to learn a lot more, because after 2 years of repairs and upgrades, the collider has begun smashing particles at nearly double the power. The things it's searching for now sound like they're straight out of science fiction. Security is tight at the Large Hadron Collider. You need an iris scan to get inside.
Thank you. You have been identified.
The entire complex is buried deep underground.
You can see power, cooling.
And this is the heart of it. Is this where the collision takes place?
The protons come down this pipe, down this orange pipe.
American physicist Greg Rockness showed us one of the 4 detectors where subatomic particles called protons ram into each other at nearly the speed of light to simulate conditions that are believed to have existed when the universe began. Is there a boom? Is there noise?
There's no noise, but there's a flash of light, and the particles fly off, and you're taking a look into the basically a microscopic view of the Big Bang.
This is what the inside of the detector looks like. It's stuffed with magnets, electronics, and sensors. Creating a miniature version of the Big Bang isn't easy. Before the particles get here, they travel through a long tunnel that Rockness took us down into during a maintenance break. For 17 miles?
For 17 miles.
In a big loop, a big circle.
In a big loop, that's right.
The loop runs beneath the countryside of Switzerland and France, not far from Geneva. The tunnel is so vast, workers zip around on bicycles. The particles zip through these pipes, guided by supercooled magnets. When the protons are going through the tunnel, it's very cold. How cold does it actually get?
It's somewhere on the order of negative 450 degrees Fahrenheit.
Is that colder than outer space?
That's colder than outer space.
Oh, it is?
Yeah.
Now, I hear that when the collision takes place, that the temperatures spike. They go way high. How high do they go?
They can be up to the order of 10,000 times hotter than the center of the sun.
No.
Yeah.
So it goes from the coldest ever to the hottest ever?
Yeah,
Like that?
Yeah.
The data is analyzed by thousands of computers here and around the world. This is what an image of the collisions looks like, with particles flying off in every direction.
Every time there's a small dot here, that's 2 protons colliding.
By carefully analyzing the data from the collisions, scientists were able to find the holy grail of modern physics, a particle known as the Higgs boson, or just the Higgs. The Higgs gives all the other particles mass. Without it, molecules would not exist, trees, rocks, mountains would not exist, we would not exist.
There are collisions 40 million times per second.
Oh my gosh. The Higgs may have been found here in the collider in Switzerland, but it was conceived in Scotland by a person almost as hard to find as the particle itself. Peter Higgs doesn't have much use for computers, email, or cell phones, and doesn't own a TV. In 1964, he was a junior professor at the University of Edinburgh when he came up with his theory. He was 35 at the time and not taken seriously.
Not many people took much notice of this kind of theory at the time. They were doing other things, which was why it was left to a few people, few eccentrics to do it.
Did you use any machines or any special equipment?
A pencil and paper.
A pencil and paper? That's all you used?
Well, that's all you need for writing equations.
Higgs' simple and elegant equation gained credence over the years, but there was no machine powerful enough to put it to the test until the Large Hadron Collider was built by the European Organization for Nuclear Research, known as CERN. Finally, the collider really did prove that you were right. And in 2012, I believe you were there at CERN.
I was there. I was more or less summoned. I was told in a message, tell Peter if he doesn't come to CERN on July the 4th, he will probably regret it.
He went to CERN along with hundreds of other physicists who assembled to hear whether the collider had proved Higgs' theory.
It was like the Olympics of particle physics. When they showed the money plot, the picture that made it clear that there was a bump, which could be the Higgs boson, there was a gasp in the audience where everyone went, oh! And it's true because it was absolutely clear that had to be something that we hadn't seen before.
I think we have it. You agree?
In the audience, the one-time eccentric teared up. This guaranteed Peter Higgs a place in history.
It's hard to tell in words.
In January, Italian physicist Fabiola Giannotti will become CERN's first female director general. She will oversee the souped-up $8 billion collider that 10,000 scientists around the world work on as they search for new breakthroughs that could revolutionize society in ways that are hard to imagine.
Is it possible that there's and I read this in science fiction, that there's a whole dimension, a dimension that we don't even know about?
Absolutely. There are theories, theory in particle physics that predict the existence of additional dimensions. String theories, for instance, they require 7 additional dimensions. So as experimentalists, we should, with our high-tech instruments like the Large Hadron Collider, just listen to nature and to what nature wants to tell us.
One of their biggest goals is shining a light on dark matter and dark energy, which are among the great remaining mysteries of modern science, and reminders of how little we know about the universe.
When we look at the universe, what we see by eye or with our telescopes is only 5% of the universe. The rest, 95%, is dark. Dark meaning, first of all, not visible to our instruments. Second, dark also indicates our ignorance. We don't know what's the composition of this part of the universe.
If we don't know what dark matter is, how do we even know there is such a thing?
We have some indirect but very strong experimental evidence of it. For instance, when we look at the gravitational movement of galaxies, these movements that are observed cannot be explained with the amount of matter that we see.
So if there's gravity, there must be mass.
Exactly. And the mass that we see is not able to explain the movement of the galaxies as we observe it.
Is dark matter here, right here, beside, all around us, all this stuff we really can't see?
Yeah, dark matter is everywhere, in this room, everywhere.
Scientists are looking for signs of dark matter inside the collider, but they have also placed detectors deep in mine shafts and in space. A short walk from the collider, Nobel laureate Sam Ting and a team of scientists received data from a $2 billion detector they have placed on the International Space Station.
The detector is in here.
So we have now a detector that's sitting on our space station.
Yes.
To see if you can see dark matter? Is that what you're hoping to do?
To see
it?
To detect the trace of dark matter collision.
Astronauts help keep an eye on the experiment.
This is real time.
Real time.
The story will continue after this.
Half a century after he first proposed his theory, Peter Higgs received the 2013 Nobel Prize in Physics, along with Belgian physicist François Englert. The many scientists who worked on the collider made this day possible. Among them, Steve Nahn, Laura Gentil, and Steve Goldfarb, 3 American physicists who have been working on the collider for years.
It mattered.
Goldfarb told us that he was amazed at how many people went online to watch the meeting at which the discovery was announced.
1 billion people by the end of that week had seen video from that webcast. So a significant portion of our planet was interested enough to watch something which was a very technical seminar.
Why do you think it's ignited so much public interest?
I think ultimately what we're doing has a lot of philosophical motivations. We're interested in understanding how things work, and I think everybody connects to that idea, and everybody's interested when science pushes the boundary of our understanding.
We're now into season 2 with a much more powerful collider. What are you going to look for now?
We have big questions, really big questions.
For instance, can they find something smaller than the quark, one of the smallest particles discovered thus far?
Is the quark it? You know, we've thought many, many times.
You mean, is it something even smaller than a quark?
Could there? It's a very fundamental.
At the moment, we think not, but who knows?
But we're still, we look all the time for that.
We looked for black holes, and we didn't see them.
Are you saying there are no black holes?
So we were looking for micro black holes that would have been, for example, evidence that there are extra dimensions, but unfortunately it doesn't look like we produce them at these energies.
But does that mean there are no extra dimensions, or that you just didn't find any?
We just didn't find them. They still could be there.
If you find a whole different dimension, will it allow us to change time?
I think this is a difficult question because scientists don't like to say that something is impossible, even if we think it's extremely unlikely.
Right. If you had asked somebody in 1900, do you think we could, take a device out of our pocket and push a button or two and talk to your spouse halfway across the world?
It's crazy.
They would say the same thing. But we can do it today, right? So who's to say 100 years from now what we can or cannot do?